Okay, it looks like we have quite a few people already in attendance. There are several others still coming on, but I think we'll go ahead and get started. Hello, everyone. My name is Jim Shaw. I'm the Director of Sales and Marketing at DTS. Thank you for joining us for the second half of a two-part webinar series titled Principles of Dynamic Data Collection. Before we get started, I'd like to cover the format and a few logistics. The webinar will be a slide presentation in audio from the presenter only. The attendees will be muted, but please make sure that you check to see the slides are visible and that you can hear the presenter. We encourage you to submit questions throughout the presentation by typing them in the Q&A window. You see a button at the bottom of the screen. We'll have a panel of experts monitoring and answering the questions throughout, and we'll try to get to as many questions as we can and answer those in real time. We'll also compile all Q&A from both sessions to send out to everyone as a follow-up after the event. This session will be recorded and made available for you to share following the event. If you attended the first event, that is already posted on our website. You can download the video and directly from our website. If there's a specific topic you'd like to cover directly in a private meeting, please reach out and coordinate with myself or our sales team. Your presenter today is Mike Beckage. He is a co-founder of DTS and our CTO. He runs our support team globally. Also on the panel, answering questions in the background, are Steve Pruitt. He's our CEO and also one of our co-founders, and Kate Martin. She runs our support team in Europe. So with that, I will turn over to Mike to begin the presentation. Thank you.
Thanks a lot, Jim, and good morning, good afternoon, or good evening, wherever you are in the world. Thank you for joining part two. And as Jim says, part one is up and available on our website. So if you missed any of the details that got us to part two, you can go back and review that. So today, I'm going to do a very quick review of the key points from part one. And then we're going to go through some what I refer to as essential knowledge for real-world challenges. These are topics that go beyond the basics, and hopefully will get you better prepared to deal with some of the real-world considerations you have to work through in order to make high-quality measurements. As we said in part one, if you're going to do a critical test, failure should not be an option. We're trying to collect data each and every time with accuracy and control of noise and aliasing and all the things that can get in the way of high quality information. And last time we discussed the fact that you should always do your homework and understand what you need to deliver when you've completed your data acquisition mission. And we're focusing in this seminar on understanding the equipment you are working with. And that includes the sensors and the data acquisition hardware. Data acquisition basics review, we went through this last in the first part, and it starts with a transducer that converts the physical world into an electrical signal. We then have a sensor interface system, sometimes called the signal conditioner, that converts the sensor output into something we can work with, digitize, and store in the analog to digital conversion section. And finally, we have a computer running software that allows us to set up, communicate with the hardware, and then do some downloading and processing when we are through. A quick review of the Wheatstone Bridge. Last time we covered sensor theory and how we are actually converting stresses in the world into strains that we then measure by using strain gauge technology to convert those real world forces into resistance changes. And we make a Wheatstone Bridge because it's the simplest way to create a usable signal out of a group of resistors arranged as a Wheatstone Bridge. Key points here are that our data recorder has to apply the excitation or the large voltage to the sensor, and then it has to take the small voltage from the sensor amplify it, filter it, and record it. And with regard to sensors, we talked about the special group of sensors called active that have built-in electronics, and they are not proportional to excitation, which is unlike the Wheatstone Bridge. So the concept of sensitivity is the relationship between the number of millivolts of output for each volt of excitation for each engineering unit. And for active sensors, it's simply millivolts of output for engineering unit. So when we look at the range of sensors we use in the physical world, we need a data acquisition because we have a need for excitation voltage. Sensor outputs are small and need to be amplified. We need filtering, and of course, we need comprehensive self-diagnostics. So the typical system in 2020 consists of a small unit that we connect sensors on one side and a communications interface on the other, and out comes our data. Today, we're going to focus on some specific parts of the DAC signal chain. This is a diagram that we covered in greater detail in part 1, but this is what we refer to as the signal chain. And today, we're going to actually focus on some sensor specifics, advanced sensor concepts, the concept of anti-alias filtering, and how that relates to analog to digital conversion, and then shunt checks. And this falls into the realm of diagnostics to ensure success. As I said, what I refer to this section as essential knowledge for real-world challenges, and we're going to start with some advanced sensor considerations. So first of all sensors have limitations on what you can do with them, and choosing the right sensor for any measurement is key to collecting meaningful data. Instrumentation that's appropriate for collecting class 1000 measurements for the automotive world and crash test may not be suitable for other test environments. And so when you're going to perform a test, you always need to understand what is the required measurement range, bandwidth of your sensor, and perhaps even whether or not you're using a damped versus an undamped sensor. We'll talk a little bit more about that later. Resonance and mounting concerns are huge, and we're just going to touch on the surface today, but I'm going to point you to some other information. And then, of course, you're recording all the signals with a DAC or data acquisition system. You need to think about the bandwidth, sampling rate, and setups. So let's get into this topic of sensor resonance a bit here. Number one, sensing devices are linear over only a small range of frequencies or bandwidths. Sensors are designed for specific measurement environments. And above their linear bandwidth, many sensors, particularly undamped accelerometers that are common in automotive and aerospace work, can resonate at very high amplitudes. Common 1000 G accelerometers have resonant frequencies above 25 kilohertz, and these are often masked by the way we digitize and filter the data. Key point, though, is it's easy to excite sensors to resonance, and we need to think about it because resonance can introduce lots of errors, including the possible nonlinear behavior of the sensor itself, and if you're not careful with setups, can actually saturate the data acquisition system, meaning clip the data if the range is set too low. In 2004, the Japanese Automobile Research Institute, called JARI, put out a report called The Problem of Undamped Accelerometers in Headform Tests. Now, this study applies not just to headforms, but to any environment where you're using an undamped accelerometer in a high shock environment. And what they found was if you look at the actual output from an undamped accelerometer, it will actually look like the blue signal here, where you can see almost 3000 Gs peak to peak at a very high frequency. However, when you filter that signal, for example, to SAE class 1000, you will actually see the tiny little filtered signal called in pink. So that's the signal you really care about, but the raw sensor signal is actually depicted in blue. Most test operators and test engineers are not aware of the high level of resonance that can occur. So it's important that we consider the difference between the raw sensor output and the actual data that we need to use to process and create a report when we're done. And to that end, in 2014, we added a section to SAE J211 that is called Appendix E, and it actually talks about many of these issues in greater detail. And we're going to touch on some of them shortly. But bandwidth, sensor resonance, and DAS considerations is something that everybody should read if you want to be suitably careful when making acceleration measurements. There's also an SAE recommended practice called J2570 that talks about sensors used in anthropomorphic test devices, or ATDs. One of the specific areas that this covers is the difference between damped and undamped sensors, showing some examples. We're not going to cover in detail the difference, but simply put, a damped accelerometer or transducer essentially has a mechanical filter inside that helps to control the resonance of the sensor. And this can be very important in making measurements in a shock and vibration environment. So on to filtering and anti-alias performance. This is a fairly large topic. We touched on it briefly in part 1, but we're going to cover some of the deeper details. But before we do that, it's important that we have our definitions of some key terms. First of all, sampling rate and data bandwidth are two different things. When we talk about sampling rates, we're referring to the number of samples per second, or SPS, that the digital data recorder is capturing. The data bandwidth is much different, and it actually means the range of frequencies over which we require accurate and linear data. This is sometimes called the bandwidth of interest, and it's normally expressed in hertz. So it's most appropriate to say I need 1000 hertz data bandwidth, and I'm going to sample that at 10,000 samples per second. Bandwidth and sampling requirements come from good engineering practice and documents like SAE J211 and ISO 6487. The current requirement in SAE J211 is that you sample a signal with a given bandwidth at 10 times that bandwidth. It's important to note that the next version of SAE J211 that's coming out later, I believe this year, requires 20,000 samples per second for class 1000 bandwidth. Bandwidth must be appropriate for the application. In automotive and aerospace and human safety applications, SAE or ISO class 1000 is generally the highest frequency that we must record. However, if you're doing acoustic measurements, blast pressure measurements, material properties at high loading rates, and even validation of computer models used in finite element analysis, sometimes require much higher frequencies. And in fact, the acoustic bandwidth would generally be up to 20,000 hertz, and some other high loading rates may require even more than that. DTS has been aware of this for a long time, and ever since 1998, all of our products have had the capability of capturing very high bandwidth data, far above the class 1000. So in the typical DAS signal chain, let's concentrate now on the anti-alias filter and the analog to digital conversion process depicted here. It's important to note that there are three types of filters that are commonly used in data collection projects. First of all, we have the continuous time analog filter. And the simplest version of a continuous time analog filter is simply a resistor feeding a capacitor, what's sometimes called an RC filter. A little bit more complicated filters are often programmed by software signals, digital signals. And this is a digitally programmed analog filter on the right, where we can actually set the filter frequency with a digital signal. And then finally, most data is post-processed using a digital filter on the PC. There are four main types of filters. All of these graphs show amplitude on the y-axis and frequency on the x-axis. The low-pass filter is by far the most common in our world, but there are different types, including the high-pass filter that only allows frequencies above a certain frequency. There's a band-pass filter that selects a range of frequencies to allow through, and then there's a band stop or a notch filter. Again, in our world, we mostly use low-pass filters. There are several types of low-pass filters, including, as depicted here, the Elliptic, Chebyshev, Butterworth, and Bessel filter. By far the most common filter type we use is a Butterworth low-pass filter, depicted in the yellow line, that has a pass band where we basically don't affect the amplitude of the signal from DC to some cutoff frequency. And then we have a roll-off zone where the signals are filtered out or attenuated. There's a lot of information on this slide, but I'm going to just say that the corner, knee, and cutoff frequency are the same thing. And this is generally thought of as the point in the response curve where the signals are attenuated or filtered to -3 decibels, which is about 30% reduction in signal. The number of poles or the order of the filter tells us how steep the roll-off is, so it would be the slope of the roll-off. And finally, there's an artifact of filtering called phase delay, which you don't really have to think about too much, but it is an important factor when we're designing a data acquisition system because it's specified in SAE and ISO documents. Before we talk more about how to apply an appropriate filter, we need to understand the analog to digital conversion process. Modern DAS or DAC are digital, but we definitely live in an analog world and always will. And what does that mean? Well, it means that signals from accelerometers, load cells, strain gauges, pressure sensors, any sensor are what we refer to as continuous time. They're constantly changing over time in infinitely small increments. But what we do with a binary or digital data acquisition system is we convert those continuous time signals into binary substitutes. And we do that by using a computer which applies base 2 math or binary numbers to store and process the data. Typically, 16-bit binary numbers are used to what I refer to as freeze the analog data points in time. With a 16-bit system, that means a string of 16 ones and zeros with a most significant bit on the left and a least significant bit on the right. And with 16 bits, there are roughly 65,500 combinations of values. The whole reason why we do this is digital data makes PC-based data processing possible. Analog to digital converters have only two fundamental properties. One is resolution on the y-axis. The resolution is the number of steps from 0 to their maximum value, and an A to D converter with more bits simply has more vertical amplitude steps available to capture a signal. The second is the sampling rate, which we refer to as samples per second. What we're trying to do is digitize the red signal, depicted as a continuously changing signal. The A to D converter can only take samples at specific amplitude levels at specific times. If we compare the top to the bottom has a higher number of bits and it's sampling at a higher rate, and therefore does a better job of capturing the analog waveform. Again, it's a digital substitute, so it has steps in it. Another way of thinking about this is higher sampling rates and higher number of bits actually reduces the uncertainty of a signal. If we draw a box around each measurement point, the better the resolution in both amplitude and time, the lower the uncertainty will be. How fast do you need to sample? I'm sure many of you have heard of the Nyquist theory, which says you must sample at least 2 times the frequency of interest. This is an important point from an aliasing standpoint, but it does not complete the picture of what we must do to minimize what we refer to as sampling error. SAE J211 currently requires 10 times the channel frequency class you care about, and the next version will require 20 times because, for reasons you'll soon see, the data fidelity is much better. Sampling error is the difference between the actual waveform depicted here in red and the data values that are sampled by a digital system. What we're seeing here is a continuous sine wave in red, and the blue boxes represent the data points captured by the data recorder with their associated uncertainties. I think it's apparent that the blue line does not perfectly represent the red line, and the difference between the blue and the red is sampling error. If we look at a sine wave sampled with 10 data points, you can see that it is possible to miss the peak value by up to 5%, depending on how the timing aligns or doesn't align. When we're sampling data, we have no control over when the signals will come into the sampling process. And so we will have some variable distortion, and again, that is what we refer to as sampling error. If we plot this graphically, where the x-axis is the sampling rate to the signal bandwidth ratio, so 10 to 1 means we're sampling a 1 hertz wave 10 times per second, you can see we have a 5% possible sampling error. If, however, we increase the sampling ratio to 20 to 1, our potential sampling error drops to 1%. Graphically, let's take a look at some real waveforms. In this case, this is a 27 kilohertz wave recorded 200,000 times a second. That sounds like a lot. But you'll notice even with that high ratio of data frequency to sampling, the data doesn't really look like a sine wave. If, however, we increase the sampling rate close to 20 to 1, well, now the data looks like a sine wave, which is what our input waveform was. If you look carefully, you can still see the digital steps in the waveform, but it's a much closer representation of the real waveform. So this leads us to the topic of aliasing, which is extremely important and must be controlled. The key point is that aliasing occurs when you digitize signals of any significant amplitude with a frequency content greater than 1/2 the sampling rate. So if you're digitizing at 10,000 samples per second, then your filter better remove most or all of the signal by the time the frequency is up to 5K. Let's talk about this from a sampling standpoint. If we undersample a waveform, as shown by the red dots on the wave here, we're sampling at a sampling rate that's too low, and then we connect the dots. The blue line represents what we record with our digital data acquisition system. The red graph is the input waveform. If we take a look at it a little differently, we're going to input a waveform of 60 Hertz and then sample it at 100 times per second. What we see is a waveform that shows severe aliasing. The problem is, if you're not aware of the relationship between bandwidth, sampling, and filtering, you can see a signal that's severely aliased and you won't know it. So that's why it's important that we minimize aliasing by using the maximum possible filter attenuation at 1/2 the sampling rate. We use the highest reasonable ratio between the anti-alias filter and the sampling rate. It's important to note that higher sampling rates make it easier to avoid aliasing. We use a good hardware filter, which of course we do in all of our products, and then we carefully control the sampling rate and filter relationship. And this is actually done in the control software. Let's move on to a discussion of shunt checks and other diagnostics. Shown here is the sensor interface for our SLICE Pro data acquisition system, and we're going to focus specifically on the shunt circuit. Shunt checks have been around for decades. As long as I can remember, test engineers have used what we refer to as the switched resistor method. In this method, we actually take a precision resistor and we momentarily switch the resistor across the Wheatstone Bridge. When we do the simple math, we can calculate the expected deflection of the sensor signal and compare that to the measured voltage. When the measured voltage matches the calculated voltage, we're confirming that the sensor resistance is as expected. We're confirming that the cabling is good and the sensor is plugged in, and it can be used as a cross-check of gain. Some years ago, roughly 20 years ago, we actually developed a concept in our products called shunt emulation. You can think of the shunt emulation circuit as an infinitely variable shunt resistor. We take a precision adjustable voltage source, we convert the voltage to a current, and then we selectively inject the current into the sensor. We then calculate the current to actually deflect the measurement channel to 100% of its measurement range. If the calculated deflection matches the actual deflection, then we have a very good check of the wiring integrity and the sensor resistance, and can have much higher confidence that we're going to proceed and get good data. This leads back to the topic of empirical checks and never assuming that a data channel is functioning correctly without a cross-check. Key point is that we want to use shunt checks whenever possible, and also if possible, we want to apply a mechanical excitation and check for reasonable response. And that's where we use the real-time display of data. When you understand the data channel diagnostic information, then you have higher confidence or troubleshooting assistance where needed. And a key point is you should never run a test with diagnostic failures reported. You should resolve those failures. We talked last time briefly how a great empirical check of accelerometers is to do a 2G roll check. So whether you are checking out an existing sensor or you just wired a new sensor, we need a reality check. Even with a 2000G accelerometer, you can rotate that accelerometer 180 degrees with respect to the Earth, and you should see a positive 2G shift. This, coupled with shunt checks, gives very high confidence that your sensor and wiring are working properly. On to the topic of grounding and shielding. A very quick overview of the noise sources in the world. There are really three. There's thermal or electronic noise that's inherent in the sensors and electronics, mechanical noise or resonance, often above the bandwidth of interest, and signals induced by interaction with the environment. When we're talking about grounding and shielding here, we're really talking about protecting the sensor wiring and the data recorder from interactions with the environment. Typical electromagnetic fields exist in all test facilities and labs in the world. We have power wiring in the walls, in the ceilings, in the lights. We're always have 50 or 60 hertz fields flowing around us. Other test devices like imagers emit electromagnetic fields. In the automotive world, airbags and pretensioners emit electromagnetic fields when they fire. A good data acquisition system has what's called common mode rejection to reject these signals, but that does not replace the need for proper shielding and grounding. Let's take an extreme example using electrostatic discharge. Electrostatic discharge is prevalent in any place where we have things like airbags opening or parachute testing, even on a dry day or a test lab that has air conditioning running, we can get electrostatic discharge. If we take an ungrounded load cell that has strain gauges on it, and we have a static discharge to that load cell, because of the fact that the sensing devices are electrically insulated from, but in close proximity to, the measured device, we'll actually have some of that signal get into your measurement devices. And finally, a little bit of that signal will make it all the way to the data recorder analog front end. And you will see a spike in your data that perhaps you won't be able to understand where it came from. This is very common in the real world with ungrounded measurement devices. You don't want to see these unexplained spikes. If, however, with proper grounding, the same electrical noise signal or electrostatic discharge is carried away to the ground, and that signal never gets into the data recorder. Very important. The proper implementation of grounding and shielding looks like this. We have a data acquisition system that's mounted to a test fixture, a vehicle, a sled, some kind of test article. Hopefully that test article is grounded to the earth. And we have a separate ground cable running from the DAS location to any isolated metal component or test device on which we have sensors. It's a very simple concept that must be followed in order to have the highest data quality. The sensor cables must be shielded, and the shield should only be connected at one end. Most sensors by design have the shield not connected to the sensing element or the metal of the sensor itself. So the shielded sensor cable should be terminated to the DAS. Key points. All DAS equipment and power supply enclosures must be grounded. Sensor cables must be shielded. When we do this and we connect the shields to the DAC ground, we are then allowing any kind of electromagnetic energy or radio frequency energy to go off to the ground and not influence the signal wiring. Don't connect the shield at both ends. If you're using test devices such as test dummies or anthropomorphic test devices, you should always use large wires between all isolated conductive parts, and then connect the entire dummy to the vehicle or sled structures and the DAS enclosures. And you have to consider cable routing. High power cables should be kept away from sensor wiring. And if those cables must cross, you should cross those cables at 90-degree angles to avoid inductive coupling. So this is a review of the slide from last time. Hopefully some of these points make more sense now. But if you understand the test requirements in standard practice and you determine the data bandwidth required and you choose appropriate sensors, remembering not to forget things like sensor resonance issues and their linear frequency range, and you choose the appropriate DAS setup, making the bandwidth, filter, and sampling settings carefully, then you can be happy with a job well done. So this gives us a better picture of everything from the sensor to the sampling process that helps us get that data we need to apply software filtering and then subsequent post-processing. Don't forget that we have the DTS Help Center available 24 hours, 7 days a week. And with that, I will say thank you very much for attending this seminar, and I will hand it back to those who may be picking up some questions.
Great, thank you, Mike. There are still a handful of questions out there. We've gone through and answered several already in real time. For those that don't get answered, if we do run out of time, we will compile and append all of the questions and answers. We'll send you a link to the file where it's located. So with that, let's stay online, and I don't know, Mike, if you want to scan question list.
Sure, I can answer a few of the ones that are open here. Yeah, so there's a question here about going to a 24-bit system help to meet new SAE requirements. And the answer is not really. 24-bit systems are often targeted toward applications where you don't have a range of available gain settings. And in the SAE realm, any good 16-bit system with appropriate gain easily meets the requirements. So you don't need a 24-bit system to meet those requirements. Here's a good question. Can I explain the common mode voltage specification for a DAS? Very briefly, all amplifiers have a range of voltages over which they can properly amplify a differential signal. The common mode range or voltage is actually simply the range of voltages over which an input signal must remain in order to be linearly amplified. That might be different from the level to which the system is protected from electrostatic discharge or overvoltage. Yeah, okay, here's another good question. When selecting the capacity of the sensor, what about considering the raw data level that would be required or versus the max filter data that we would expect? And that really gets to the heart of the sensor resonance discussion we had. You have to really look at the specs of a sensor, particularly an undamped transducer, and make those DAS setup decisions very carefully. And I'll give you an example. In some headform impacts, we are looking for data that will never exceed 500 Gs. But if you know that an undamped accelerometer may resonate at plus and minus 2000 Gs or even higher, that would indicate you should set your full-scale range much higher than your filtered, expected filtered data. This is actually addressed in Appendix E of SAE J211, if you've got the latest version. So I would strongly suggest you look at that. It's another good question. When we calibrate a data recorder, a DAC, what is it that we're doing? Well, the simple definition of calibration is comparing a measurement system to a reference measurement system. So first of all, when we calibrate, we take reference equipment that's calibrated and traceable and compliant with ISO 17025 practices, and we compare its signal measurements to the measurements making with a data recorder. In our systems, we actually store the calibration parameters that tune the calibration in non-volatile memory. And so calibration means we compare a reference to the data recorder we're calibrating, and any adjustments get stored in parameters inside the data recorder. So that's what we do. That's how we tune it. Okay, I'm scanning. Okay. Oh, okay, here's one. Every time active sensors are mentioned and ARS is shown, I did that because it's our sensor and I don't want to, endorse other manufacturers selectively. So when we talk about active sensors, there are many different active sensors in the world, and that includes accelerometers from companies, like Diatran and Endevco and Kistler and PCB. In the automotive crash world, that would include sensors such as the IR track, the optical displacement transducers. It would include any sensor that has a very high level output, which means it has an amplifier built in. So there's a whole range of transducers. Some of the most common ones are things like low G triaxial accelerometers and such.
Okay, Mike, I think we're close to the end of our time here. For those questions that did not get answered live, we will, again, compile the answers to those questions and get those out to you shortly. I think with that, I will wrap up. Mike, we really appreciate it. And again, we appreciate everyone attending either one or both of the sessions. They'll both be posted. And if you have any further questions, please don't hesitate to contact us directly. Thanks again, everyone.
Thank
Appreciate
you.
it.
Thank you so much for attending.